Okay, let's talk some more about these chemical reactions, these chemical changes that take place all around us. First of all, a bit more on communicating with one another about them. When we are trying to express what's happening during a chemical reaction, we write that as a chemical equation. Let's talk about an example. Let's talk about my car. Now, no, this isn't my car, but it certainly has something in common with just about every car I've owned. It's rusting. So what happens when something rusts? Well, the iron metal that the car is made of reacts with oxygen gas in the air. Those two combine to make rust, which can be relatively well described by the compound iron oxide. So this is the chemical change that's happening. Iron combining with oxygen to make iron oxide. Of course, that's a very cumbersome way of putting this. We need to be able to be much more concise, much more effective communicators. So we use chemical equations. They look something like this. Let's have a look at the different components that make up this chemical equation. Right, first of all with the terminology, you can see here on the left-hand side what goes into our chemical reaction. We call these the reactants. The arrow here shows us where the change is, so it separates our reactants from what we get out of the chemical reaction. And what we produce during this chemical change, we call these the products. So reactants on the left side going into the reaction, the products on the right-hand side, they are what we get out of the reaction. When we've got more than one reactant or more than one product on one side, we use a plus sign to join the two together, just to show that they are two distinctly different chemicals. When we're trying to describe the chemicals that are involved, we just use the molecular formulas that you and I have already spoken about in previous topics. So Fe, that's just iron atoms or pure iron metal. O2, that's the molecular formula for oxygen gas. And Fe2O3, that's the molecular formula for iron oxide. You may also have noticed there's some extra numbers in front of our chemicals here, these coefficients. They tell us how many of each atom or molecule is required in order to make this reaction work. So I need 4 iron atoms, 3 oxygen molecules, and that will give me 2 iron oxides when this reaction is complete. And finally, one last detail that I'm sure you've noticed, after each compound, after each material, I've got a letter in brackets. These are the states of matter for each of the different compounds or elements that's taking part in the reaction. S for solid, L for liquid, G for gas, and I'm going to introduce a fourth one, to which I'm sure you're immediately pausing and saying, hang on, there's only 3 states of matter. The fourth one is a bit of a combination of the two. The fourth state of matter you might see is called aqueous. We use the symbol AQ for our state to denote it, and aqueous means a solution made by dissolving something in water. There are lots of examples of aqueous solutions all around you in your day-to-day life and certainly in the lab. Taking a few everyday examples, drinking water that you get from the tap. It's predominantly water, but there will be small amounts of salts and organic materials dissolved in that water. The seawater, the ocean, much better example. All kinds of salts and minerals dissolved in water. Soft drink or cordial, if you take the average soft drink, it contains water primarily, and into that we put carbon dioxide and sugar and flavours and more sugar and colours. The amount of sugar in soft drink is frightening. No wonder it tastes so good. These are all really good examples of solutions. One material dissolved in water. So we will use that fourth state quite frequently when we're discussing chemical equations, chemical reactions. Now, we're going to use these chemical equations to show us all kinds of really useful things going forward. They are an incredibly powerful tool for chemists. But before we do that, let's quickly talk about just a few things they don't show us. So, here's my car once again, rusting away. One thing we cannot tell from a chemical reaction is how fast the reaction goes. Why does my car look like this and not like this, or even like this? No indication of how long it takes to get there. Also no indication of how far along that path we are. Is my car in the first stages of rust or the last stage of rust? And finally, it doesn't tell us how we get from start to finish, only where you start and where you finish. Of course, if we understand how a chemical process happens, we might be able to do something to change it, to either make something not happen or to create an opportunity for something to happen that otherwise might not. So there are some things that a chemical equation doesn't show us, but there is also an awful lot that it does show us, which makes them really useful for us to have. Come back in the next topic and we'll talk about how we can assemble and balance our chemical equations.